Okay, so it's a pleasure to have Nikita Nekrasov with us today. There was no good reason to introduce Nikita yesterday, much less so today. Okay, so just the floor is yours, and please continue and entertain us. Okay. With the second part of his introduction to the geometry of relativistic hydrodynamics.
Right. So let's try to stay in the flow. Unintended. So let me recapitulate where I stopped yesterday. I made a claim, which today I want to expand on. The equations of relativistic hydrodynamics, which were developed in the last century by Lichnerowicz and Carter and others, actually represent something, a geometric fact, which is that there is a inside some auxiliary phase space, which I will review. We are seeking the points of intersection of two almost half-dimensional subvarieties. One of these subvarieties, which I call quasitropic, only knows about the geometry. By geometry here, I mean just smooth structure of the form manifold, the space-time of which the flow is propagating. And the second subvariety is Lagrangian, and it depends on the choice of the space-time metric and a function called the energy density, which is for the purposes of this talk, I will take the minimal choice. It's a function of two variables, which are times equal E is the function of the density of number of particles, which is a scalar, of course, four-dimensional scalar, and entropy, which is also a function. So this space in which this encounter of these two subvarieties takes place is just a vector space of dimensional. It's a space of 0, 1, 3, and 4 forms on the form manifold. So they have notations and they have names. So the 0 form is called S and is called entropy. So it's an entropy at each point of space and each point of time. So it's per point of space-time. P is a 1 form, it's called momentum. N is a 3 form, and it's a flux. It's a flux of the number of particles. So if you take a three-dimensional submanifold, let's say it's a space like submanifolds, when you integrate n over submanifold, it tells you the total number of particles of fluid which you have at your disposal. And finally, mu is a 4 form, so it's a kind of a density in space-time, which so far didn't have a good name. It's a value on the Lagrangian submanifold, which represents the equation of state, is equal to the product of local temperature and the density of particles. So I don't know what's the name for that. So it's some kind of a temperature per particle or something. But it's a 4 form. And when I call it the ambient space, so the points of that ambient space, we don't actually experience that. So it's something which exists in our imagination, and it's useful for describing the solutions of equations of motion, but we don't obviously have an access to the points of that space unless we can change the space-time metric at will. And so the picture which we are going to explore is that inside this space, so we have two interesting subvarieties. Actually, this one better. I have a picture. It looks more like a cone. Okay. Then so
I see Pm is a finite.
Infinite dimensional.
Finite
Everything is
dimensional,
infinite. Everything is infinite dimensional. Infinite dimension.
So
Infinite.
what does it mean? That you have a submanifold and so on.
So it's infinite dimensional spaces. We have infinite dimensional
It's a
subreddit.
delicate
Very, very
matter.
Yes, yes, of course. So P is the space of fields. But it's a vector space, so you can, if you like, you can endow it with the topology of a Hilbert space. So it's actually you can. If you like functional analysis, we can be more
The
detailed
problem
about.
is when you have to take so-called symplectic structure, and then it becomes more delicate.
Well, it's a symplectic structure and defined using the
Integrals.
yes, integrals. So
Integrals exist.
yes, but that's well the to define the symplectic so the symplectic structure will be so the one which I write in this form. What I mean by that, so it's a two form, right? On vectors, so on tangent vectors to the space, but because the space is vector space, the tangent vectors are the same thing as the points of that space. And so to give you the value of this two form on two vectors, well, I just need to compute, this is a finite dimensional integral.
So this makes sense if you take a piece of M, which is compact.
Well,
it
makes sense if if you like, of course, it's a restriction on the type of fields we allow, or more precisely on the types of fluctuations or deformations of the fields we allow. So let's say that these are L2. So if they are L2 type fields, so you can say that delta S, delta mu, delta Q, delta S belong to these are differential forms, but of L2 type, then these integrals will exist. M doesn't have to be compact.
Boundary conditions and the infinity.
Or decay conditions, or right. So there are some, of course, there are some refinements which are needed, but so the point is that so the first subvariety, so the C, it's a subvariety, which means that now I'm not considering all possible fields S, P, and nu, but only the ones which obey additional equations. And so these equations will be the differential equations made of simple type, rather simple ones. So these equations can be described geometrically as setting to zero the moment map. So what is the moment map? It's the map from my symplectic manifold, so Pm is the symplectic space, to the dual space of the Lie algebra of the group, which
Pm is not only a manifold, but it is a vector space, is it?
well, it happens to be a vector space, but what's important here is it's a symplectic manifold with a group action. Okay. So the moment map is defined in the case where you have a symplectic manifold with a group action, and this group action preserves symplectic form, then with additional, so then what you have, okay, so let me just describe the general.
So
The general sector. So you
not
can
preserve the vector structure.
okay, so the group, in our case, the group will act by linear or affine transformation. So it will preserve, well, maybe not the vector structure, but at least the affine structure. But the general case where the moment map can be defined is for a symplectic manifold. there is a group. It's a V group. Denoting omega. So it means that for every vector field, for every element of the Lie algebra, there is a corresponding vector field. And the fact that it preserves symplectic form means that the contraction of this vector field with symplectic form is closed. And usually, so we impose the additional requirement that it's actually exact. So it can be written as a differential of a function, and this function is linear in psi. So the collection, so the assignment to every vector, to every element of the Lie algebra, I get a function on manifold, which is the Hamiltonian. The additional requirements, namely that the Poisson brackets of those functions produce a function of that type corresponding to the commutator of the corresponding elements of the Lie algebra. So this is some condition on the choice of constants in solving this equation. So this equation doesn't determine mu uniquely. You can add a constant, and there are nasty situations where there is no way to obey this condition. There is always some correction term, a cocycle. In our case, it will not be the case, even though we're in two-dimensional situation. But there might be cocycles coming from the boundary terms and maybe from some issues with divergences. So let me ignore that for the moment. The point is that, so there is this kind of algebraic construction. So to every element of the Lie algebra, I give you a function on the manifold. And so this collection can be viewed as a map from the manifold to the dual space to the Lie algebra. So this mu now has no indices, so it's for every point of P, I got a covector of the Lie algebra, such that if I take a vector in the Lie algebra and contract this covector with this vector, I will get the value of mu of psi. So this is called the moment map. To give you an example of the moment map, example. Let's take the finite dimensional manifold, the cotangent bundle to the Euclidean space. The group G will be the group SO3, which acts by rotations. This is the space of that is X. So the moment map is the map from P to the R3, which is the dual space of the algebra. And it's given by the vector product. This is why it's called the moment map. It's from this example. If I view this, it's a vector valued function. So each element, each component of this vector is a function on T star of R3. If I view this function as a Hamiltonian and look at the vector field this function generates by this rule, the corresponding vector field will be the rotation, one of the three basic rotations. So this is the origin of this whole construction. So in our case, the group which I want to explore first will be different dimensional. So all I'm doing and what I'm doing is the stretching of these notions.
Sorry, Nikita. May I have a question about this group? Because of course it's infinite dimensional from the point of view of linear algebra. But if I were to think of these as sections of a certain bundle over M, this would be this would have this Lie algebroidal feature to it. And if I were to integrate the Lie algebroid here, it would be something like dimensionally downgraded Hitchin's generalized tangent bundle. So tangents plus Whitney plus M times R. And since I have a form on PM, on which the group, as you call it, acts, it's kind of natural to have an extension of the tangent as the symmetry structure. And then, sorry, if I may just, so if I were to think of these as more like sections of a Lie algebroid, as it happens, it would be a trivial one, pretty much. A Lie algebroid over M, I would ask about the integrability of this Lie algebroid, and I would try to understand the quotient that you're trying to take in terms of the homotopy model, right? I mean, of the corresponding groupoid, which would probably be something like Weinstein's symplectic groupoid. I'm just shooting, but the question is whether I can integrate these symmetries that you have, because I look at how the functions act. And the functions act like, it's more like a symmetry algebra, not a symmetric group. And I'd be tempted to look at the integrated version, which would be bisections of this Lie groupoid.
Here, it's a bit misleading. Well, misleading. Yes, there is a bit of a coincidence that the Lie algebra. So this factor is that a billion. The group is a billion, and it coincides with this Lie algebra. Well, I don't know. I mean, I don't know.
What I'm saying is that you look.
Well, maybe the difference. Maybe the group actually is doesn't act quite freely because the constants don't act.
But the group doesn't. How it acts doesn't matter so much. I mean, so for the better. But my point is that if you look at the sigma model, two-dimensional sigma model,
yes,
where on the target space you have an extra structure of a cohomological type like omega here,
yes,
which is the Calle-Bramont 3 form. Then what you see as rigid symmetries, infinitesimal ones, are sections of Hitchin's generalized tangent bundle. And for the gaugeability of these, you need some kind of weak Dirac structure spanned by these. And then you integrate this weak Dirac structure, and it gives you the action Lie groupoid, basically. So this somehow, somehow that's the association that I keep having since you introduced this. What you call the gauge group looks like a hybrid.
Gauge group, yeah, because it's a group which simply acts on.
No, right, but yeah.
I'm not gauging it, but you see, I'm not.
Well, you'll be taking the quotient, and for me, the quotient is.
So I discussed the quotient as a measure of how this coisotropic subvariety differs from Lagrangian. So the quotient measures, the deviation from the CM being middle dimensional, but it's not what I'm to take when I study hydrodynamics. See, in hydrodynamics, this group action is the flow. So we're actually interested in
precisely the opposite direction.
Right.
Okay.
It's kind of opposite to what usually to gauge theory, which for me as a gauge theory is quite frustrating. But that's what. I mean, somehow the chemistry of this underlying fluid is what breaks the symmetry, and that's what. So, I mean, we can talk about this. Somehow, it looks like the fluid is trying to take a quotient, but it takes it in an old-fashioned way by sort of gauge fixing. And the gauge is these groups, the symmetry is fixed by imposing the equation of state, which I will review. And that seems to be the physical essence. It's not like the other contexts where we identify things related by the symmetry formations that we just got care of the gauge choice. Here, gauge choice is the essence. But it's true that one can. So I will discuss maybe connections. I will discuss certain connections to gravity. And from the gravitational point of view, of course, this group is a kind of poor man approximation to the symmetries of GR, which involve diffeomorphisms of a high dimensional space. and more than just diffeomorphisms, like convergism, something like that. So this is where the algebraic and groupoids should appear, because the actual structure, which acts by symmetries, changes from point to point of the phase space. So it could be that the equations of hydrodynamics are just an approximation to the better structure. We'll get that. Let's just start with simple things. we'll gradually we'll try to be more sophisticated gradually. So so what is this group? So it's a group which is a it's a group. It's a set. It consists of pairs. Objects. G is the diffeomorphism of M, and F is a function. And so diffeomorphism for complicated group functions just viewed as an abelian group, additive group. And there are two ways of making this group act on PL. This acts. So diffeomorphisms act geometrically. As in mu. Just by pull that. But the functions, there are two choices. It's kind of interesting to discuss these choices, even though eventually on the open dense subset of PM, these choices are equivalent up to diffeomorphisms. So in one choice, looks like we're doing just gauge transformations, albeit with the non-compact gauge group. So I'm just shifting the one form by exact form. In another approach, I'm shifting the one form by the exact form times the zero.
Well, either non-compact or basically you sit in the algebra. That was my association. That somehow you seem to be sitting in the with the functions, with the function.
Right, but somehow it's I'm combining them. And I'm using both G and F. Right? So since for diffeomorphisms, it's natural to view them as group.
Yeah, sure.
For these guys, I'm also kind of forced to think of them globally. So then here, something like that. I may commit some errors with signs. Sorry. TF. So what's the difference between these two choices? So the second choice preserves the linear algebra, the linear structure of P. So these transformations are linear in S, P, and nu. So it is some kind of rotation. So this preserves the vector space structure of P, which personally I don't really care much about. In the first choice, this is a fine transformation because P is shifted. But so in that sense, this capital PM, I should not really view it as a vector space. It's like an affine space. But anyway, both transformations preserve this symplectic form. And so they define some, they might come from a moment map, and indeed they do come from a moment map. So this moment map should take values in the space dual to the Lie algebra of this group. Let's discuss what is this space. So first of all, what is the Lie algebra of this group? Well, it's a direct sum of the algebra of vector fields plus again the same functions. Now, what is dual space? Let's do it. So what is dual to vector fields? Because point-wise, the object dual to a vector is a one form. But I want to have a function also. I want to produce a number. I should be able to produce a number out of a vector field. So in order to do that, I need to take the one forms and then tensor them with 4 forms. So something which will give me a density when I contract with a vector field, which I can then integrate. Again, so either I should work on compact manifold and then everything is smooth, or I should work with or I could work with compactly supported functions and forms, or I could work in L2 category. So there are all the refinements which might change the story, but and then the guys which are dual to the functions are just 4 forms. So this is the dual space. So my moment map should take values in this sophisticated space. The tensor product is over functions. So it's well, it is what it is. So eventually you learn to work with these objects. So if say pi is an element of that space, you can write it locally as pi mu dx mu from 1 to 4. So then these coefficient functions, pi mu, they are not functions, they are pseudo-scalars. They are actually, you should think of them as 4 forms. In other words, if you change coordinates on your manifold, in addition to the usual Jacobian, which comes from the transformation of Zx, these pi guys, they also pick up a Jacobian, the determinant of the Jacobian matrix. So they have slightly more sophisticated transformation. Okay, so now the moment map takes values. So in this direct sum, it has 2 components. So it's easy to compute the component corresponding to this abelian bar. And for the first type of transformation, it is just the derivative of the 3 form, Dn, which is the 4 form. And for the second transformation, it's derivative of S times n. So this it's straightforward, and this is the straightforward analog of what we do in Maxwell theory. Just remind you.
Well, you assume M to be oriented.
Do I assume M to be oriented? I'm not sure.
Because you integrate forms.
Yes, so what? So M being oriented just means that there exists a 4 form which doesn't vanish. So what? It might be that.
No, not orientable, but oriented. I mean, you have to fix the orientation to be able to integrate forms instead of density. Yeah, so you were. I mean, it's a subtle choice. I mean, if you,
I don't think I choose. I don't think I have to fix the orientation. It's a.
then you don't.
If I fix the orientation, then I could trade my 4 form mu for a function.
So you should explain what is the duality between Lie algebra and its dual.
Okay, so the duality.
So for the take the functions, keep vector fields.
So
and
let's take a vector field, right? And I have a function.
Yeah.
And now let's say I have phi belong here. And, what kind of measure do we can use? Let's say lambda belongs here.
Okay.
So the value of pi lambda on the side is equal to integral m of contraction of v with pi plus psi times lambda. So the contraction of v with pi, what do I mean by that? I mean that I contract the vector with 1 form here,
Yeah.
and the result is a 4 form.
So you have 4 form.
So the result is a 4
And
form which
you
I'm integrating
integrate 4 form over manifold.
over many.
Means manifold should be oriented.
Orientable.
Oriented.
because then I mean you integrate forms or over oriented spaces. Otherwise, there is the sign ambiguity. This is. I mean, it might not matter, but it is there.
It differs but by a sign. You should have not forms but densities.
Density, and then you can forget.
Like square root of GMU. And
No, but I don't want to. No, I want to. So I will introduce the densities later when I introduce. So if I introduce the metric, I will introduce a particular density. But I think at this point I can work with arbitrary forms. I'm not sure. Okay, but
No, we can probably skip
let's
this matter.
keep
I
it
mean,
like
everybody.
Yeah.
You know, what to do to improve.
Okay.
right. So yeah, maybe you're right. Maybe I didn't pick an orientation. Although, okay, suppose I pick a, so suppose M is orientable. So suppose I pick an opposite orientation. So I can redefine. So I will redefine my forms by just changing sign of mu and n,
Yeah,
and nothing
this
will
means
change.
that- Yeah, and this means.
Sure, let's move on.
Okay, so.
yeah.
But so this is what I mean by so this
Sure.
this is how duality works. Okay? So pair. So there is a little computation you do which produces the generator in the sense of moment map of the action of the group of diffeomorphisms on this forms. And so the first term is here. So it's a 1 form ds tensor 4 form mu. Okay. The last term is also clear. It's 1 form p tensor dn, which is a 4 form. The middle term is a bit tricky. So what do I mean by that? So n is a 3, but I can also view this as a vector field tensor 4 forms. So this is the physicist would say it as follows. So if I have a 3 form, then mu lambda. So I can associate a vector field by raising the indices with a totally antisymmetric index. So I call this guy n check upper row. So it looks like a vector field, but it's not exactly a vector field because if I change coordinates, it will be an additional Jacobian of the coordinate change, which is why there's this. It's what?
It's density.
It's vector density.
The vector density.
No, density is transformed with the absolute value
But
of the
vector
Jacobian.
density transforms.
This is just the top form.
Okay.
It's a top form. So I mean, what we're quarreling about is whether there is a sign of the coordinate change or no sign. So for me, there's always a sign.
There's a sign.
The absolute values, they come later when we introduce things like metrics and things. Why do I care about this? Because this part can be defined over any ground field. I don't have to work on real categories. I understand it's not interesting for hydrodynamics, but it might be interesting for other purposes. So that's why I don't like to introduce absolute values at this stage. So this is purely algebraic. Anyway, so now so this is so n check is the same thing as n, but just viewed with a different hat. It's like it's a vector valued in top forms. And so I contract this vector with a 2 form dp. I produce 1 form, but because this n hat actually carries this 4 form piece, the result is also 1 form as a 4. Okay. Much ado about nothing. Now the question is that the claim is that outside the hypersurface in my four-dimensional spacetime, where this quantity in brackets makes sense and is non-zero, if I impose the moment map for the group of diffeomorphisms to be 0, then it follows that the moments for the 2 versions of the scalar action are actually agree. So if one of them is 0, then the other is 0 and vice versa. There's an interesting locus when this vanishes, but let me stay away from it. Okay, so notice that I talk about hydrodynamics, I talk about fluid motion, but I didn't have any vector fields so far. And it turns out that there are many vector fields one can define using our data. So and it's interesting because in the literature, people kind of impose all sorts of constraints and try to solve all sorts of equations at the same time. And so there is one vector field people talk about, but in reality, there are several, and you can talk about them. So if I'm somewhere here in this space, I just have a collection of 0 form, 1 form, 3 form, and 4 form. No equations imposed. I can define several vector fields on spacetime, all more or less algebraically, but there is a little bit of physics to it. So there is so-called canonical vector field, or canonical. This is not my name. It's just, I think Carter introduced it, and it's called canonical. So now everybody has to use this name. And so this vector field is defined roughly as a ratio of 3 form over the 4 form. So it's just that if you have 3 form and you can ask, is there a way to produce it by acting on the 4, contracting with the 4 form with some vector field? As long as nu doesn't vanish, and that's what it takes to be a fluid, that there is some density which doesn't vanish everywhere in space-time. There's no emptiness, right? This vector field is well defined. So what this vector field does, if you look at the integral trajectories, then at each point, this trajectory is tangent to the kernel of the 3 form. It's a kernel. If you have a 3 form, if it's non-zero, in 4 dimensions, it has a 1-dimensional 0 subspace, and now you can not only orient the subspace, but you can also kind of choose a particular parameterization with the use of the 4 form. So that's one vector field, it's algebraically defined. Another vector field, which is Hamiltonian, you define by solving the following variational problem. So suppose I want to find the extremum on the space of parameterized trajectories of the following functional. So this functional consists of 2 terms. I take the image of this map and integrate P over this image. So here it is oriented because, so this interval, there is direction in the sense, this notion of this local time increasing. So that's why it's oriented. So I'm integrating 1 form P over this trajectory minus integral over the interval dt times the pullback of S. So this functional might resemble something from yesterday. It is the usual functional we extremize in Hamiltonian mechanics, just that we usually write 1 form not as P, but we call it PDQ. But this P is, since it's a 1 form, I can write it as so it's a 1 form on the 4 manifold. And so the extrema of this functional are the solutions of the Hamilton equations, so S is down the road. And in terms of forms, this is just solution of the equation ds is equal IVS dp. So this is well defined when if I'm outside the locus where the 2 form dp degenerates, then this equation can be solved. So Vs can be written as dp inverse as z. So now these 2 vector fields, I can, so given SP and nu, I can define 2 vector fields. And the claim is that this point belongs to this quadratropic subvariety, v equals to 0, is equivalent to the condition that v is equal to vs. So these two vector fields, which are defined by completely different formulas, nevertheless agree. And the linear derivative of v with respect to v of nu is equal to 0. So these are two conditions. So this is a geometric characterization of this quadratropic subvariety. It looks simpler than solving the equations. By the way, these equations mu equals to 0 are called Lichnerowicz equations. Even though he meant something else, but so the main claim again is that so we have two subvarieties, one I just described, and another one will be Lagrangian, and which we'll describe now. And so the intersections of these two subvarieties are the flows bring relativistic the equations of relativistic hydrodynamics. So this vector field V, it's a space-time vector field. So it has components both along the time direction and the space direction. If you want to project somehow this flow to the flow we could perceive, like we perceive things, time frame by time frame, we should write it in some gauge as a function of by dt minus v plus v. So this v would be the Euler vector field. This will be the vector field in three space dimensions, which depend on time.
Yeah.
Yes.
M is a momentum map, yes? Mu is
Yes.
momentum map.
Yes.
So the orbit of 0 is
The pre-image.
isotropic inverse image of 0. But if you take another value, it is no longer
No longer.
coisotropic. It's
Right.
only because 0 is an orbital of the quadrant action.
Absolutely. Yes.
Yeah. So what happens if we are interested in these other values of mu?
Very good question. So, in order to answer the question, you need to provide me with the quadrant orbit.
We are ready.
Okay. So,
And what kind of topic?
quadrant orbit.
Because he said we are ready and pointed at me. I don't have any orbit in my disposal.
So, I think yesterday I discussed the issue of the quadrant orbits of the smaller groups, which are the groups of three-dimensional diffeomorphisms preserving the volume. And these are already pretty sophisticated. But if you ask about the physical meaning, so what will happen if instead of saying writing mu equals to 0, I introduce additional degrees of freedom, which represent those orbits?
We really need quadratropic submanifolds.
Yes.
It's inverse images of orbits of the conjoint action.
Right. Quadrant orbits. So you could, instead of nu inverse of 0, one could look at nu inverse of some orbit. So this is in the. So the physical meaning of that, I think, would be the hydrodynamics of material fluids. So when you have some additional fields which are carried by the fluid, and so the degrees of freedom of these additional fields will be represented by this orbit. But I don't really have any good examples of those, except for maybe something which is localized. So there are orbits where things are associated with submanifolds of M. So imagine that you have a point, or maybe a surface, and the surface can move around. But so you see once again, so this guy sits in this space, which is the space of one form tensor omega 4 plus omega 4. So it could be that your orbit is such that this part is 0, but this density is singular. It has it supports some points. Or it could be that, and this is something I will get to later, that the one form which this guy represents is singular along the codimension 2 surface. So there is some kind of vorticity which is supported on a two-dimensional surface called vortex sheet. So these are interesting things. We'll mention that. Another thing where this becomes relevant is this theory of quenches. Just mention that. So this is the situation where you have a regular flow, then suddenly, somebody hits the water with a hammer or something, and then nothing happens again. So this moment of sudden change is corresponds to a smallish quadrant orbit. Okay. So the most important part from the point of view of engineering is this Lagrangian submanifold, which now depends on the metric. So it has parameters. One of the parameters being the metric. Now G is not the diffeomorphism but the metric. And for physical applications, we actually fix the pseudo-Riemannian metric, so the Lorentz signature metric. But formally speaking, I could also study Euclidean or Riemannian metrics. And now, what do I do? So I write this functional on the space of n's and s. So this is the density. So this is now the density. So this is the square root of minus g of x. This is the volume form associated with the metric, and ng is the norm. It's a pointwise norm of the three form defined using the metric. So this is the formula. There might be a minus sign under this square root, but I'm sure I ever drew it correctly. So what do I do now? So this is a functional of half of my variables. It only depends on s and n. It doesn't depend on p and nu. And what do? I now impose the relation, saying that p is the variational derivative of this function with respect to n, and nu is the variational derivative of this function with respect to s. And so that defines submanifold, infinite-dimensional submanifold in my space P, where P and nu are related to S and N. Now, practically, what it means is that you introduce yet another vector field, in fact, vector fields out of SPN nu data using the metric. And so one of them is, so they're called Landau. Landau introduced one vector field, but I refined this definition just for the moment. So one is you take the three form, you apply the Hodge star using the metric, you get one form, you raise the index using the metric, and then you divide by the norm so to get the union norm vector. And another choice is to take one form P, raise the index using the metric, and divide by the norm of this one form. And now these two vector fields are equal on this Lagrangian submanifold, because this relation guarantees that P is proportional to star of n and n is proportional to star of n. So this U is usually called Landau field. This is the vector field which you find in textbooks of relativistic hydrodynamics. So recall that on the space of solutions of the equation mu equals to 0, we have this relation that if I denote by little omega the derivative of p, then we have this equation which says that the field V is Hamiltonian with an M if omega is a symplectic form, with Hamiltonian being S. So somehow the space-time, we don't usually think of it as a phase space, but it becomes kind of spontaneously becomes a phase space for some auxiliary mechanical system. And that's a system, and so the trajectories of the fluid particles are the Hamiltonian trajectories, where the role of the Hamiltonian driving the flow is played by the entropy. And as usual in the Hamiltonian dynamics, there are canonical invariants. So the periods of the canonical one form PDQ over the contours are preserved if you transport the contour by the flow. And so this is known as Kelvin's theorem, which originally was, of course, found for the Euler equations in the non-relativistic case. But then the reason Carter introduced this vector field V and called it canonical was that he observed in a complicated way that the circulation of momentum is preserved by the flow, by the canonical flow. So this is not true for Landau velocity. So if you transport the contour using the vector field U, it will not preserve the circulation. The reason is that, so of course, V and U are proportional to each other, but the coefficient of proportionality, which is roughly speaking the inverse temperature, depends on space and time. And so when I'm saying I'm transporting with the flow, it means that I'm solving the equation, this equation. So there is some time, which is it's not astronomical time, it's just a way of parameterizing the flow. And if I solve this equation or I solve this equation, even though geometrically I have the same trajectories, but I get to the same point on the trajectories at different times. So the contours will be transported differently. So that's why canonical flow is in a sense better than the Landau velocity. Okay, so why am I excited about this presentation of the hydrodynamics equations? Well, that's because the study of intersections of Lagrangian submanifolds is something we do in Floor-Fukaya theory. So this is a subject of interest for topological strings. So it means that if CM were not quadratropic but Lagrangian submanifold, then this would be the problem of finding vacua for some kind of A model defined on this manifold P. Well, you could say, well, CM is not Lagrangian, it's quadratropic, so then why being excited? Well, that's because there are other types of topological strings, not A type, not B type, but the so-called C type, the ones which are responsible for the deformation quantization of Poisson manifolds. There is something called Poisson sigma model, which can be promoted to a topological string, and that has as a boundary conditions has quasitropic submanifolds. So there is an interesting problem of studying maps of strips to Poisson manifolds in general, such that one boundary lands on the quasi-tropic submanifold, and another boundary lands on the Lagrangian submanifold. And so the configurations of low energy will land at intersection. So that's connecting this problem to the
Yeah, but that if I may interrupt.
yes.
So precisely, let me go back to my
So
question,
that's-
because the Poisson sigma model has Lie algebroidal symmetries, and they will induce something on the boundary, which, if I understand correctly,
All I'm saying is that the good old problem of relativistic hydrodynamics is just one of the terms in the in the infinite package, which is produced by the L-infinity morphism of from the functions from the polymetric fields on the space field.
but my point is also that if I'm not wrong, this is sort of something that I understood relatively recently, is that if you kill an obstruction in the Poisson sigma model, there is a flat jerk obstructing an integration of its Lie algebroidal symmetries to Lie groupoidal symmetries implemented by bisections of the groupoid, whose tangent Lie algebroid gives you the symmetries. Then you would have some kind of Lie groupoidal symmetry on the boundary. That's why I asked the question.
Yes.
Yeah.
So, so good. So, there are other questions one can ask in this geometric context, which may or may not have interesting consequences for the hydrodynamics. Okay, so anyway, so this is something which mathematicians love and develop. The fact that so there is Poisson sigma model, so there is a study of maps of something two-dimensional into this phase space, and the phase space is defined. It's a functional space defined over M4. Means that overall, this comes from some kind of a reduction of a 6D theory on M4 cross two-dimensional street. So there's an interesting six-dimensional theory hiding behind this. I will not venture a guess what this thing is. So that's maybe high up in the sky. Let's go back to something down to earth. I started with Euler equations yesterday. So where are the Euler equations in all this? Well, they're simply a particular case of the structure where M4 meets foliation or time-like slicing. So if you take M4 to be a product of a three-manifold times a line, then you can decompose all the forms accordingly, and you decompose the canonical vector field the way I wrote before. And then the moment map equations with these identifications will become precisely the Euler equations. E dot plus LB plus sum rho I d equals to 0, and then rho I dot plus rho I equals to 0. So these are precisely Euler's equations written in the form of the quadrant flow, and the relation between pi rho to v mu is the inertial map, which is hidden now in the equation of state. Okay, so if you go to the actual talks of physicists working on hydrodynamics, they tell you that we don't know what hydrodynamics is, but we know it is a study of conservation laws. And so they usually tell you that, well, you should write a stress tensor and then constrain its form using some arguments and symmetries, and then write the equation of conservation of stress tensor. And so far, I didn't mention once what the stress tensor was. So let me now explain what it is. And this is something which comes from the traditional classical mechanics problem of having not one Lagrangian submanifold, but maybe a family of Lagrangian submanifolds. Suppose now, in our case, the parameters which we can vary are the parameters which enter the definition of Lagrangian, which is the equation, the energy function, and the metric. So let's vary the metric. If I change the metric, my Lagrangian submanifold will change because the equations connecting P and N depending on the metric. So we'll do some flow. And so Hamilton and Jacobi tell you that of all possible variations of Lagrangian submanifolds, the variations which come from the Hamiltonian flows on the ambient space are described by the Hamilton-Jacobi equation. So the generating function of my Lagrangian was called A, and the Hamilton-Jacobi equation, which we usually write in this form. And so what does it tell me? It expresses it tells me how the generating function of the Lagrangian submanifold changes as I perform the flow in the ambient space. Okay, so what kind of flows can I perform? Well, I have this group G4. And so if I make an infinitesimal transformation associated with the element of this group, so I start now acting with my, let's say, with diffeomorphisms on the ambient space. Remember that Cn being the zero level of mode map is invariant under the action of this group G. But my Lagrangians, they're not. In particular, because if I apply diffeomorphism, general diffeomorphism, the metric, my generic metric G will become some other metric. Infinitesimally, it will go to something like I is epsilon plus epsilon 0. So this is the vector field. Now, the Hamiltonian question is precisely the moment map for the action of the group of diffeomorphisms, convoluted with epsilon. And so this is the variation of the generating function of the Lagrangian subvariety with respect to the one of the infinitesimal diffeomorphisms, that is vector fields. And so the equation says that this change, which is the change in components. So this is the change in the generating function. This is the left-hand side of the Hamilton-Jacobi equation, is equal to the actual value of the Hamiltonian restricted on the Lagrangian submanifold, which is this moment map convoluted with epsilon. Okay, so it's some identity, it's something. But now if I'm sitting at the intersection point, so I'm not sitting anywhere on Lagrangian, but at the actual point representing the flow, and I perform this change, then on the intersection, mu vanishes. And so my identity is that to the first order in the arbitrary vector field, the generating function of the Lagrangian corresponding to the equation of state doesn't change. So from that, if I define the stress tensor, essentially the variation of, so it's not the variation of an action per se, but it's a variation of the generating function with respect to the metric. Then this identity will tell me that I have the usual covariant conservation of stress tensor, which, as you know, in the absence of isometries, doesn't mean any conservation at all. It's just some identity. So here the logic was kind of reversed. So we start with some first principles and we derive this equation. And usually people put some guesses for T mu and then write this equation, and then from that they derive the equations of hydrodynamics. So I don't know about your taste, but in my taste, this is simpler and kind of more systematic. Okay, so that I explained. This is the actual shape of the stress tensor, which you get from this particular derivative function. So it's a conventional fluid stress tensor. My time is probably up. You're all tired. Let me just mention, but since there were some questions about algebroids, let me just mention a cute point. So where in life have we met this group diffeomorphisms, semi-direct product with functions? Here is where. Suppose that you're, for some reason, you're interested in Einstein theory, but not in 4 dimensions, but in 5 dimensions. Suppose space-time was 5-dimensional, and M was actually space. So then if you want to treat the Einstein theory canonically, you would say, okay, let me take M to be space, let me associate to this spatial slice the phase space, which is the cotangent bundle to the space of all metrics, which now I would have to perform a symplectic quotient with respect to the group. But what is the group? So the group, the gauge symmetry of GR are space-time diffeomorphisms. But if I'm sitting at space, what I see are spatial diffeomorphisms and something extra. So there is some constraint which physically comes from revolutionization of time, or if you like, normal direction to M inside the 5-dimensional manifold. But from the space point of view, when I'm just looking at the space of 4-dimensional metrics, I don't recognize this additional symmetry as coming from some kind of diffeomorphisms. I just have its generator, which is quadratic in the momenta, which is called Hamiltonian constraint. And people who look quantum gravity try to make sense of it quantum mechanically. Size-wise, the group whose moment map we are imposing in this context is the same group. It is the group as semi-direct product of the 4-dimensional diffeomorphisms and functions. Here, of course, these functions are kind of infinitesimal functions, so it's hard to say whether it's an actual group or it's a real algebra, because we don't really know if I have a space slice and time changes a little bit, whether my space slice will remain to be diffeomorphic, to be the same, or maybe there will be some transition and space will change completely. And in GR, we have to treat all such transformations as symmetries. So in that sense, in GR, the symmetry structure is not a group. It's but maybe it's a group of coborgisms. I don't know. So this 5-dimensional picture and analogy is kind of useful because it allows us to write the equations which I was writing in a more compact form, and also kind of package the fields. So I had S, P, and nu into a smaller set of fields. So from the 5-dimensional perspective, you only need one form and the 4 form, which I can do pair. And so the decomposition of if let's say the 5-dimensional manifold is a product of M and circle, small circle, then the group which I was using in this case can be viewed as the group of diffeomorphisms of this 5-dimensional manifold which commute with the circle rotations. It's not the full 5-dimensional diffeomorphism, but it's a subgroup, and so it will look like so the difference with what I was talking about here would be that the functions on M will be replaced by the circle valued functions. So it is some kind of modification of hydrodynamics. That's what I'm saying. Now, of course, there is important difference between the gravity problem, GR, and hydrodynamics. This is the count of degrees of freedom. We discussed it yesterday. I will not talk about this. the topology changes which I mentioned. So in gravity, life is richer than just direct products of 4 manifolds times R. And in relativistic hydrodynamics, one should probably allow for topology changes, and that's related to the question about the non-zero levels of moment map. So one reason is the somewhat mysterious proposal by Onsager to impose the quantization condition on the momentum, saying that the circulation around any closed loop should be an integer in the units of Planck constant without bar. And so if you generalize this idea, you might allow some loci in spacetime where this integer remains non-zero even when the counter is extremely small. So it means that the field P becomes singular. So dP develops the curvature singularities. So this is something which we do in gauge theories when we introduce so-called surface defects. Here it's either they're present in nature, so that it's small at sufficiently microscopic scale, the grainy nature of fluid becomes important, or it's a quantum effect when you have superfluids and things like that. So if you take this seriously, then you would add those sheets as degrees of freedom. And so this would extend my phase space PM from the space of forms to contain also these dynamical surfaces. And this is somehow similar to how we go from gravity to M theory, where we add.
Or from Chern-Simons to Chern-Simons with Wilson loops, right? I mean, there you.
Chern-Simons with Wilson loops it's yeah, maybe something like that. This is a kind of better understood problem because that just means that you add an extra field. You just add charged fields. In M theory, this is mysterious.
No, I'm not.
But
Just
in hydrodynamics,
technical.
it could be that we just add additional fields which I didn't think of yet, and so then those fields will represent those non-trivial quadrant orbits of the group of diffeomorphisms. Okay, maybe I should stop. So there's some things about other topics, including viscosity and the quantization, which maybe some other time. So this is another souvenir from India. So the most interesting puzzle from this discussion is that it looks like the most natural place for the covariant hydrodynamics is in 5 dimensions, 5 space-time dimensions, but we live in 4. And so why is that? Well, there's an answer in Hinduism, which I will tell you if you ask me after the talk.
Okay. Thank you very much. There have been quite a few questions along the way, but
Yes,
if there are any
people can have
further questions, then please shoot.
This 5-dimensional approach, is it a Kaluza-Klein type?
So it's type. So this decomposition. So this is Kaluza-Klein. This is Kaluza-Klein type in the sense that there is no dynamics which sort of squeezes the phase dependence to be trivial, but it's some kind of symmetry. But it's Kaluza-Klein's type in the sense that you interpret extra fields as coming from by decomposing fields living in high dimensions.
Okay, further questions? I'll have a question about this relation to Poisson sigma model, but we shouldn't keep people with that. So if there are no further questions, then let's thank Nikita for a very pedagogical and patient explanation of the details. Thank you very much for a nice talk.